Okay, so we are ready for our second talk. Hippocampal network interactions reveal a dual process framework of human navigation from Zhili Li, who's at Fudan University in Shanghai. Thank you.
Thanks, everyone. My name is Zhili Li from Fudan University. I'm the first year of PhD student in Dennis Lab. So today, I'm so happy to be here to share my recent work in spatial navigation in humans. So humans, they rely on spatial navigation for both routine and goal-directed tasks in everyday life. So for example, spatial navigation, finding our way home or navigating a new city like Brisbane, or just like hanging around the campus, they all require a complex set of behaviors to get what we want. And spatial navigation also supports essential cognitive functions like memories, attention, decision-making, And the neural basis for spatial navigation has been a topic of investigation across several animal and human studies. Importantly, these studies have identified the hippocampus, especially the anterior hippocampus, as a key region in helping us to generate a global representation of our surrounding environments, or also widely known as the cognitive map. Despite this evidence, the processed brain-wide neural mechanism underlying spatial navigation requires further investigation. So additionally, a large amount of studies have been previously emphasized that we do not all navigate in the same way. So some of us use map-like strategies, and while others rely on routes or landmarks. And similar to other prior studies which investigate the individual differences in such as like personality or intelligence or creativity, the study of individual differences in navigational style may also allow us to have a better understanding in the neurobiological basis of spatial navigation in humans. However, the current definition of navigational styles lack precision and neurobiological groundings for them to be a useful descriptor of human navigation. For that purpose, in this study, we first aim to identify robust and reliable decomposition of navigational style, and then to investigate the association between individual differences in navigational style and intrinsic brain connectivity profiles, particularly that of in the anterior hippocampus. So for this, we firstly collected a large-scale behavioral data using the Santa Barbara sense of direction scale. So it's a commonly used questionnaire that captures one's ability to form a mental representation of space, preference for like using external aids such as using the physical map to navigate, or the confidence in navigating unfamiliar environments. So in addition to an in-lab and online participants, we also included open access data set to improve the generalizability of our model. So well, can we get the model? We then apply the orthogonal projective non-negative matrix factorization to extract robust behavioral components across the region, across the rating of 562 participants. So OPNMF is a robust and interpretable factorization method that capture positive covariance within questionnaire data. For example, it has been successfully employed in the classification like in schizophrenia subtypes and their neurobiological differentiation. Here, we use the OPNMF to obtain interpretable components of navigational style. To make the model robust and generalizable, we also applied a cross-validation framework during this decomposition. And in the subset of 166 participants, we also acquired an HCP style resting state fMRI data across 2 runs to enable the estimation of individual-specific functional connectivity profiles. For this, we selected the anterior hippocampus as our seed region of interest, based on prior research highlighting its key contribution to spatial navigation. And in a general linear model, we then investigate the link between intrinsic functional connectivity profiles and navigational style score by the non-parametric permutation testing using PALM. And to further characterize our results, as you can see below, we also quantified the distribution of connectivity profile across the brain networks, as well as projecting them onto the principal connectivity gradients. And here comes the result parts. Firstly, across 562 participants, OPNMF reviewed a 2-component model which shows the best stability and generalizability, while in factor 1, items related to self-location, mental map, and spatial memory, which can be interpreted as a memory-based navigational style. The second factor, as you can see here, it reflects one's confidence and preference for using external tools to navigate, like a physical map or just landmarks. So having identified these 2 robust navigational styles, our next objective was to investigate whether they showed a distinct relationship with anterior hippocampus connectivity. So for the memory-based navigation style, higher component scores was positively associated with stronger anterior hippocampal connectivity to the posterior cingulate cortex, medial frontal cortex, and angular gyrus, as you can see in the left-hand side. And you probably can also tell from the distribution of connectivity profile across YAO7 network on the right-hand side. And this region largely fell into the defoldable network, which plays an important role in memory-guided processes. And conversely, higher component scores for tool-based navigational style, which also was associated with greater connectivity between the anterior hippocampus and inferior parietal cortex and the fusiform gyrus. At the network level, on the right, and this region fall within ventral attention network, dorsal attention network, and frontal parietal networks. Together, these regions have been recently proposed to make up a kind of action mode network, which is important for goal-directed behavioral. And in summary, we identified 2 robust data-driven navigational styles with distinct brain connectivity profiles. And the memory-based navigational style adapted by mental mappers engages the hippocampal defoldable network connectivity axis to support an intrinsic spatial representation. And for tool-based navigators, or we can call it strategic planners, a hippocampal action mode connectivity is recruited for perceptually based processing for spatial navigation. And together, these results highlight the flexible connectivity profiles of the anterior hippocampus in supporting distinct style of spatial navigation. However, we should keep in mind that these 2 styles of navigation are not an either-or situation, so people generally use both strategies to navigate, and also will change the styles while under different circumstances. So in the future, we would like to further investigate the dynamic connectivity profiles of the anterior hippocampus during performance of real navigational tasks, and to study the effects of aging and pathology on this system. And that will bring to the end of my talk. I'd like to thank my supervisor, Dennis, and the Cognize Lab team for their support, and as well as Clark and McGuiles for sharing their question data. Thanks also to the China Brain Project for funding. I'm happy to take any questions, so your feedback will be really helpful. Thank you. And here's my poster number. If you want to have a chat with me, you can come tomorrow. Great to see you. Thank you.
We have time for questions. Yes. Can you come to the center? Just, yeah, thanks. That's probably better.
Maybe
yeah.
in front. Will be.
Fantastic talk. I thought it was really interesting. I was wondering if you were interested in doing any kind of task-based fMRI, like maybe getting people to navigate through spaces with particular directions and seeing how people of different profiles react to that information. Do you have any thoughts on that? I'm just interested.
Yeah, that's a really good idea. And in our lab, we are just thought about that, like doing any task. There is a paradigm that we have already adapted, and we think whether we can adapt this kind of navigational tasks in the fMRI scanner, and that's really the next stage what we want to do. Yeah.
Perfect. Thank you so much.
Thank you.
Yeah, please come.
That was a great talk, thank you. I couldn't help but realize like the two maps that you showed seem to be complementary. So like wherever it's blue, the other mode is sort of red and vice versa. Is that like a surprise, or is it like mathematically because the two factors are also normal from the design of the matrix is going to be expected?
Yeah, so these two maps is in a way just to correlate with the component scores with the connectivity of every voxel. So these two distinct patterns may also relate to the decomposition stage, like what we used in the NMF. So they are not like, the component scores are not like an orthogonal way, so that might be, so that these two kind of scores, yes, they correlate with each other, but not in an orthogonal way. That's what makes it seems like this kind of pattern. But as I just mentioned, so people in these two styles, they're not like opposite to each other. So this can like we think it makes sense. So yeah, thanks for the question.
Thank you.
Great.
And we have a question on the audience response. So you focused on the anterior hippocampus and provide a good justification for that, but did you see any other connectivity patterns with other parts of the hippocampus, or did you not look at that?
That's what we want to check. So this is only a seed region based on anterior hippocampus, as you said. So it's a really good idea. And at the next stage, we might with these two kind of navigational style scores, we want to look at a brain wild, like every voxel and every subcortical like regions we will check in the brain wild, not only the anterior hippocampus. Yeah.
Okay, great. Thank you.
Thank you.